section of bay, and you just dial over, push it, dial I mean, stuff that goes in the thing is 20 years old.
It's got to be try to figure out how to connect the dots.
All right, I think we'll get started again. The guy went for coffee. I'm going to he has a general class, so I'm going to do things that general classes already know. So he won't miss one. Let me just talk about some of the symbology of what we've talked about so far. We talked about resistance, and that is a resistor. Okay. We talked about batteries. That's a battery. We talked, and has a V, or usually I use V a lot more than E, but people have different preferences. What else were we talking about? There is something called a coil, which has a coil-looking symbol, and we use L for the coil. And not to be confused with the battery, there's a capacitor. So both the lines are the same length, and sometimes capacitors have a curved line and a straight line. These are capacitors. So now let me get into the resistance of one of these other elements. So now we're going to be talking about AC resistance. Straight resistance, R, works for DC or AC, all the same. Same Ohm's law will tell you how much AC gets through or how much DC gets through. It's the same. However, if you have these other elements, mainly inductors and capacitors, they react with frequency. So they will have different amounts of resistance. It's actually called reactance. So here, the thing that is keeping the current from flowing is called resistance. And it is frequency agnostic. It doesn't care what frequency is going through it. It's always the same resistance. These things will inhibit the flow of AC current. And then by AC, I mean RF, AC, voltage, anything that's oscillating. And it's that, quote, resistance to the flow is called a reactance. And reactance tells you that it's affected by frequency, and it changes with frequency. It's not always the same for everything. So resistance is R. Reactance, we usually use an X as a symbol to show that we're getting a resistance to a frequency. I don't know if Rich usually tells you the equations for those. I'll put it down. You probably don't need to know it. But this is getting into kind of a different kind of mathematics, a complex mathematics that I'm not sure if you need to know it or not for ham radio tests. So J is the square root of -1. It's an impossible number. It's called an imaginary number. Omega is frequency, but it's a circular, it's a frequency, it's not in hertz, not in cycles per second, but it's a circular frequency. How many times the thing goes around the circle. And the relationship is omega is 2 pi times f. 2 pi is the circumference of the circle. And f is the frequency. So frequency, the omega's units are radians. And frequency units we call hertz after a man named Hertz, which stands for cycles per second. Now what does that mean? Cycles per second. Most things that we deal with are sine waves. Sine wave looks like this. That's one cycle of a sine wave when it comes back to where it started. And then it just repeats after that. Second one, third one, and so on. These cycles are moving through the air. And if you stand in a single spot, the number of cycles that go by in 1 second is your frequency. So the cycles per second, so this is one cycle. And it's also one wavelength. So if you're standing in a single spot and you can see these radio waves go by you, if you can count them real fast, you can tell how many cycles per second, how many hertz, what the frequency is. The cycles are also spread out. They're moving at the speed of light this way, but they're also spread out. And if you can measure from this point to this point physically, that's the wavelength in meters or feet or whatever you want to measure it in. So the important thing here when we talk about these is that the relationship, there's an inverse relationship between frequency and wavelength. Wavelength, which is we use a lambda symbol for, is proportional to 1 over the frequency. The faster the frequency, the higher the frequency, the shorter the wavelength. This is one of the most important concepts that you're going to run into in radio. Why? Anyone have a guess?
Your antenna has to,
It's related to the wavelength.
to the wavelength
So
for efficiency.
if you want to be reasonable, if you live in the suburbs, you don't have a lot that's capable of putting up an antenna that can handle 60 hertz or even 1,000 hertz. There are ways around it, which you'll learn later, but if just a straight antenna is 1/2 of a wavelength. Okay? So if your wavelength is, well, we were just talking in the break about the lowest the lowest frequency that amateurs are allowed to use is the 2,200 meter, a meter being about 3 feet, band. That's, the signals in that band have roughly a wavelength of 2,200 meters in the air. Okay, that's pretty far, right? So 2.2 kilometers, like somewhere almost a mile. Okay. That's 136 kilohertz. Now I'm throwing around a lot of kilos and megas and whatnot. You should have the sheet that looks like this. This will help you understand what all these words mean. So kilo means 1,000. So 136 kilohertz is 136,000 cycles per second. That's how many things pass by you. Your telephone, 850 megahertz roughly. Mega, a million, 10 to the 6th. So 850 million cycles pass by you in a second with a cell phone. Gigahertz, the Wi-Fi frequency, 2.4 gigahertz. 2.4 billion, 10 to the 9th, 2.4 billion cycles pass by you in a second. When we talk about the ones on the bottom with the negative exponents, milli means 1/1000th. Micro is 1/1,000,000th. Nano is 1/1 billion. And gets smaller beyond that. Another place where you might go a little bigger is, anybody got it's called a terabyte drive? That's 1,000 times a billion. It's a terahertz. Terabyte. So 1,000 times a billion byte. What's real small? Pico. I don't know if I can give you an example from life on nano and pico and femto, but they're really small. And we tend to go up by thousands. So every one is 1,000 times or 1/1000th of the one next to it. Okay, so we have this relationship between wavelength and frequency. So let's talk about, let's see if one of your sheets has got some examples. I don't know if it does. Oh, here's a few examples on this thing. This is a general license examination. Just to give you some relationships between wavelength and frequency. Just some examples. Hams use the 10-meter band. 10-meter band is roughly 28 megahertz. You don't have that?
I don't think you can pass it out now.
Oh, okay. That's all right. Just for some examples, because this is just, oh, he's coming around with us now. So the 10-meter band is about 28 megahertz. We go to a longer wavelength, 12 meters. Now 10 meters is about 30 feet. You can build an antenna 30 feet long pretty easy, but it's half of that. It only needs to be half of a wavelength, so 15 feet long. 12 meters is about almost 25 megahertz. So the frequency has gone down, but the wavelength has gone up. 15 meters, about 21 megahertz. Frequency still going down, wavelength going up. Now, 17 meters, 18 megahertz. 20 meters, very heavily used band by hams. It's a really good band for long distance communication. 14 megahertz. So now 20 meters is like 60 feet. So an antenna would have to be 30 feet long. A full-size antenna. It's getting pretty big. There are methods to shorten them, but in general, the lower the frequency you go, the longer the antenna. Let's go down to 160 meters, which is not the lowest. It's about 2,000 kilohertz. That's just above the AM broadcast band. So 2 megahertz, 2,000 kilohertz, 160 meters. 160 meters, let's do the math in our heads, is about 480 feet. So an antenna, a full-size antenna would have to be 240 feet long. That's pretty long. That's probably as big or bigger than most lots in the suburbs. So it's going to be really hard for you as a ham radio operator to put up a half-wave piece of wire for that band. like I said, it doesn't keep you off that band, it just.
It has to be a vertical run,
No.
so you can wrap it around.
There are all kinds of little tricks that you can play. The vertical is part of it, folding it back on itself is another part of it, and using inductors to shorten the antenna is another part of it. But just for simplicity's sake, just so you have a feeling for those bands, the ones that have the easiest antennas for the best propagation are the ones that get used the most, 20 meters. It's a very doable antenna. When you do walkie-talkies, ham radio walkie-talkies, they usually start up around 2 meters, 144 megahertz, 145 megahertz, 6 feet long, 3-foot antenna, it's easy. And the little rubber antenna on the end of most walkie-talkies, inside of that is a coil of wire that the full length is your 3 feet. Doesn't work as well, but at least you can carry it around with you. Okay, so that concept is a very important one and greatly affects the way the signals are used. Okay, now the next thing I want to get into, now that we've introduced these concepts for resistance, or reactance, now we can deal with full circuits. What happens when you start putting different elements together? Okay, maybe I should erase a little.